Okay, hello guys, how you doing? So, like you can see, this first question. The integral on the left is so basically they are talking about this integral. This integral, we call this the line integral, not the surface integral or the volume integral. No, use the line integral. So here, the integral regard to chosen volume is not the volume. If it was a volume, it would be like this, but it's not a volume. With the kind with the little v, but it's not that. So surface integral is also not a surface integral, also not a surface integral. If here it was writing like a line integral, like this, it will be correct, But in this case, with a surface integral, it's not correct. So it's not correct. Then you have the next one is correct, and that's not a loop. Okay, next one. Part B. Part B. The current along the path in the same direction as the no, because when you have a loop, your I mean your B is always tangent on your loop over on your path, always like this, always be so always on tangent on your loops, and your your current is not in the same direction as your magnetic field, because if I do like this, it means that my current is directed like this. It means just that my current is out of the page. I will show you what I mean. Imagine you have a right hand like this, then just this one is just the finger is going to curl like in the direction of my magnetic field like this, and then you have my thumb. You're just going to be out the page, like that's current, that's the B. So it's curling in the direction of the B, and that's my current. This is the demonstration, so. So okay, next one. G. The circle under integral means that B area must be integrated, not over a circle or a sphere. Over a circle, yeah, but it doesn't have to be a circle. Along the path of a closed physical direct conductor, yeah, but not only this, over the surface bounded by current carrying a wire, yeah, but it's not only this. It can be any closed path that you choose. So this is the most correct answer. Which of the following choice of path allow you to use Ampere's law to analytically find B? So yeah, the path must pass through the point radius. I mean the red array, sorry, the array. So my array is like that's the center. That's the rate. That's the distance of the R. So basically, my path must pass through the point. So the point is like here. I mean, it means it has to be here. On the grens, on the bounded place. Um, this so situation one is correct. B of I mean the option A is correct. B option the path must have enough symmetry so that B and D L is constant along large part of it. If B and DL are constant, it means that they have to be on the same direction like this, parallel to each other. So basically, this segment of my length is also, it's basically that, they're in the direction, same direction as B, you know, same direction. So basically, you can also say that this one is equal to B times L, and then you can say that it is equal to mu null times E, just like that, huh? Just like that. Okay. Next one. Okay, the path has to be no, doesn't have to be a circle. Doesn't have to be a circle. Don't forget that. I will erase it for confusion. Umbrella lobes can be used to analytically find the magnetic field around a straight current carrying wire. Yeah. Suppose just that this was just an I will maybe use this. Suppose that this was a current wire, maybe more circle or maybe more, and in a current wire you can find your magnetic field, with the Ampere's law, so it's true. Ampere's law can be used. Ampere's can be used to analytically find the magnetic field at the center of a square loop carrying a constant. Never in the center. No, never. You can never find here the magnetic field only on the bonded parts. On the begrenzte part of the circle or of the vierkant loops or in any loops, any part that you choose, but not on the center. Then you have part G. Part G say Ampere's law can be used to analytically find the magnetic field at the center of a circle. The center you can never find your magnetic field here. No, never. So false. Ampere's law can be used to actually find the magnetic field inside a toroid. A toroid is a donut shaped one and family with many turns of wire. Okay, so toroid is like, yeah, like they say that, in form with many turns of wire. So doesn't have it's I say true because it doesn't have a center, I mean they have a center, but the center is just filled with many turns of wire. So I mean there's not center. So I say true. But if you want to learn to read some at like explanation, you can read this on below. Then you have this part. Okay, this part you have to use your right hand, like so basically I will show you what I mean. So basically we are here, wire 2, and maybe I will go like this just to show you more what I mean. So wire 2 is going to be like this, I mean, I don't know if you can see. No. Imagine that your wire 2 is under. I mean, that's your wire 2 under. And so that's wire 1 to the right. And that's your right. Damn. So wire 2, wire 1. Wire 2 is going to curl like this. And it's going to come out like in this direction, And so it's gonna be in A, it's gonna be out the page. Wire 2. Wire 1 is gonna be also damn. So it's gonna be curled like that, and it's gonna be out of the page too, because I said I did like this, if I continuously turn my finger, it will be like, like this, off the page, you know. For B, also that's A off the page. I will be yeah. Okay. So yeah, B. So here we have B. I will show you B here on my screen. And demonstrations like that. So my wire two, as we know, is going to be like this, That's wire two, that's wire one, you know. So my wire two is gonna turn like this, It's going like this. It's gonna be out of the page in B. This one, huh? And then you have wire one. Wire one is like this in B. So we have wire two out of the page in B and wire one in B. So basically there is like two different direction, and two different direction is opposite. I mean, opposite direction. So basically it's zero. Then you have part C. What is the direction of the magnetic field B at part C? So you have your wire one. It's gonna be in C. So C is basically here. So wire one in C. Okay. Wire two is going also in C because wire two is like turning like that, and instantly it's going to be in C, in C. Wire one also in C. So this two is gonna be into the screen. So here. Okay, next one. Then you have part A. Part A. So basically they say which one of these four, which one of these four figures or more a good demonstration for this figure. So I choose B because I saw this more in my theory, but we will see. What I can say is also that B outside is always zero, and B inside is always a strong magnetic field. Always a strongest magnetic field. So basically, you always have to be a part one that's in the solenoid, and other part is out of sight of the solenoid. The weaker one and the strongest one, zero, and maybe it have some numbers amount of strength of magnetic field here. So B, part B. So basically they say, okay, yeah, assume the loop B has a length L along K. What is the loop integral in the upper in Olympus law? Assume that the top end of the loop is very far from solenoid, even though it may not look like it in the figure. So that the field is assume that to be small, it can be in yours. So basically what they say is so they say just that we have to use what can I say? So this one is L, L and B are parallel. So it's just, I mean, they just want to tell you that, and what I did is like a V, Toi aussi, tu me cherches, hein. Tu sais pas que je suis en train de faire une vidéo là, tu. Okay, so basically, yeah, basically, if you have B and L in the same direction, you get this, you get this formula, But to be in solenoid, where you're being, yeah. The next one, part C. What is physical property does the symbol E enclosed represents? Um, this one, because B, B and L, they don't have to be B and E. So E is basically out of the page. Yeah, out of the page, and that's in the page. Out of the page, in the page. So they don't have to, so it's false. The current interpret in the opposite direction, false. The total current passing through the umbrella in the either direction, it's false. You can only say that way, yeah. Total current passing through the umbrella loop in either direction. Now, the net current stroke the umbrella loop, yeah. That's a good one. Here's the last one because this one was more specific to every current that passing through the loop, and that's a total current passing through the no. We are just looking for the total current, the total current, not the total current in each one direction, each direction. No, not the minus direction, minus current or the plus current, positive current. No, just the total current. So per D, what is the what is the current close? The current passing through the chosen loop. So the current passing through the chosen loop, like that's my chosen loop. The current passing through the chosen loop, yeah. Is okay, so you basically have to know which one. Okay. My previous formula was not this one, but it was this one. Just basically we had this times dl is equal to, because it is chosen loop, so it's basically this. Basically this one. But if you want to know what B is, then it have to be that. Okay, because I feel like B don't have to be here. Also, it's just a magnetic field in just one loop, And there was also another formula for the solenoid. It's like B is equal to times N times E. What you can say here is that you can make this two equation equal, and you can find them this one, because this one and this one gonna be with this also, and what you have is alone these four things, and that's E, that's E, and you find two E's here, N and L. I mean no, it was the L there. The E, oh, it was E, the solenoid. Maybe I have to raise it for the confusion. So this one is E. Okay, next one. E. Basically, what I try to say is that you have to. This is just the formula for the magnetic field for solenoid. For solenoid, that's this formula. And what you have to know is that N is just we call this the number of turns per unit length. It means like N is equal to N over L. So the number of turns and the length, that's one. Part F, what is bait out? So basically they say just that I bait out is here, or here, but not in this thing. So it's zero, always zero. It's out. So zero is here. G, what is each of the following condition must hold allowed to use because the only location where the distance from the dance is many times Z. Okay, yeah. So basically they will choose a location where you can find much magnetic field going like this. Consider any location inside the plane as long as L is much longer. Doesn't have to be A, doesn't have to be B. Consider only location along the axis of the solenoid. Doesn't have to be C also. So A, A is very, very, very important. Next one. So the next one, oh yeah, it's a little bit like flex, but not really like flex. So basically you have one H is X, then you have Y, it's a rectangle, that's a rectangle. So what they say here, which of the following change will induce an electromotive force in the loop when you consider each option, assume that no other change occurs. So what here can happen is that your magnitude B can increase and can decrease, but you can also rotate it like about the vertical axis, and you have the horizontal axis, So basically, well, I will show you for the equation. So basically they say that if this was my rectangle, and most of the match field is going to be coming like this, So what you have to do is that my loop can rotate it in the vertical axis. This I mean like this, or in the horizontal axis around horizontal axis, horizontal axis, vertical axis, rotation. This can be influence the magnetic field. Okay, part B, find the flux B through the loop. So basically I said just that it's so the flux is either everyone have to know that it's B times your area. I will put this like this, area of the rectangle is just x times y times the b, then if you flux, then you for searching your source, I mean EMF in volt. So what you have to do is just like so flux, I mean x times y, so it's basically the flux divided by the time is equal to your EMF, your volt in voltage. Don't forget that in voltage. Then you have D. Okay, this just intermagnetic field steadily decrease from B to 0 during a time. The situation. What is the magnetic E of the induced current? Express your answer in terms of X, Y, B, T, and the resistance R of the wire. Okay. So basically, if you know that that this one is also involved, then you can also know that R times E is equal to this thing, And what we also can do is that if you want to look what E is, you can do like this. Just basically this, you know. Okay. E. So yeah, basically they say just that let me show you. Let me show you. So my B is gonna be um out of the pitch, and so that's my rectangle. You know, I don't know if you can see this. That's my point B. So uh B to 0, it means that my and I say counterclockwise. Why? Because if you turn in the counterclockwise, it's gonna be turned like this, you know, and B, you know, is gonna be nowhere. So it's decreasing 0. But if you are here in the, let me show you. If you're here, part F, they say which of the following change would result in a clockwise EMF in the loop. So it means that if we were here now, and so my point is that my V have to be increasing. So what I'm going to do now is like my rectangle is gonna move in the clockwise, you know, and it clockwise where I say that because clockwise is here mentioning, you know. So in clockwise, it means that my B is going to be increasing, you know. That's my B, you know. I mean, that's my B. So rectangle was like this, clockwise, you know. But imagine it was like, you know, it's also counterclockwise, I think. Yeah, so it's basically going up, you know, and then clockwise, you know. This is the idea that you have to, you know, to understand it, you know. Okay, next one. Oh, the next one. Oh, next one. Okay. For this one, I just did like this. So you have your 3 fingers. I know that I will show you better maybe. So we have here my V is like this direction. Then I know that my B is in this direction, and my first is like offside, you know. So B and V have basically the same direction, you know. I mean, no. B is into the page, and B is the right side. And that's my first, you know. So basically, what I say is that induced current flows counterclockwise in the U shaped. I mean, you know. So basically, what I say is that I just imagine that my thing was like moving like this, or what is later this. I was just pretending that my thing was moving like that because it's always gonna be like this, you know. That's why I choose the first one. I'm not sure it's correct. Okay, that was it. Close the camera. Hope you understand it. It's just, you know, the last one was just that, you know. But I hope you understand it. You know, I'll see you to the next video then. Ciao, ciao.